Hello,
Hello, how are you?
I'm fine, sir.
What happened yesterday?
Yesterday I got into accident.
Oh, accident ah? Is it serious?
No. Accident, not that kind of accident. It's just when I reverse time, I hit that young, and then the car, like the outer part, all like kena.
So finally you get it settled lah.
Yeah, I went to go fix the car lah. But thank God nobody got hurt. No other car got kena lah. So it's only my car.
Okay lah, as long as everything is okay. Anything you want to ask?
No, sir. Sir, you have your phone with you, sir.
Yeah, I have my phone. Anything?
No, then my car like kena like this lah, sir. So, yeah.
You knock into it or what?
No, I reversed and then I knocked into it. Wanted to
Okay.
come out.
Accident
Oh,
lah.
my bad. And then that's why I had to cancel class lah, sir.
So finally, what did you do?
Finally, my grandfather took it to the service. Not service center, the car mechanic place there, and then asked to fix lah.
Oh, your grandfather help you lah. Okay lah, good lah. Okay, anything?
I didn't want to
anything?
move the car lah, sir. So yeah.
So the car is
I
okay
called
lah.
him immediately. Lucky engine, no problem. It's just the bumper only got kena lah, sir.
Okay, okay. As long as everything is alright lah, no problem lah.
No, it's only that left part lah, sir. So there's nothing much. Nobody got hurt lah, sir.
Okay lah, as long as nobody hurt. Anything you want to clarify before we start?
No, not really, sir. I've been watching the videos. Now I can like understand better lah, sir.
Okay lah, good. As long as you can understand.
Slowly understanding. Sir, the phase difference, right, sir, for chapter 20. Do they ask it frequently?
Chapter 20, any problem?
No, the phase different. I always see they like to ask this calculation, the 5 over 2 pi equals to x over lambda.
All this formula you
I like to see they ask that a lot.
You have to do the past year paper, then you know what type of question they will ask you. I finished topic 19, topic 20. So I'm now working on 21 past year question. Okay, let us go to our worksheet 25 to review what we have learned.
Okay.
Let us just review what we have learned.
Now, yeah.
Same teacher.
Same. Yes, sir.
Okay, worksheet 25. Before we finish another topic today, radioactivity. Okay, can she should we see worksheet 25 now? Page 57. Can?
Can.
Okay. What is binding energy? Just review.
What is binding energy? Binding energy. Binding energy is the energy required to break up a nucleus completely.
Not enough information.
Right?
Either the energy released when the nucleons come together to form the nucleus, or the energy required to separate the nucleons into its individual components. Okay? Distinguish between binding energy and chemical energy. Don't think they will ask you lah, but anyway, it's good to ask you lah. Yeah. Nuclear reaction, binding energy is released when nucleons combine to form the nucleus, while chemical reaction, the energy is smaller, involve the bonds that is broken or new bonds form. Okay.
Okay.
What is mass defect? All this must be in your head.
Mass defect is the difference between total mass of nucleon and mass of nucleus.
Okay, mass defect is the difference in mass between the total mass of nucleons, that means proton and neutron lah, in the nucleus and the nucleus itself. Does the neutron has binding energy? Explain your answer.
Does the neutron have binding energy? No.
Right? It's a single particle. Unless you combine with neutron and proton, then you have binding energy. But neutron is a single particle, so it has no binding energy. Okay?
Okay.
Okay. Have you calculated that? Use E equals mc square. The energy in 1 kilogram. What's the energy in 1 kilogram? E equals mc square. Calculate out. What the answer? If we convert all the mass into energy, what is the energy involved? Yeah, should be able to get 9 times 10 to the power 16 joule. Okay. Number 16. A 60-watt heater heats an insulated metal electrically for 10 minutes. Calculate the change in mass. Okay, first calculate the energy supply. Right. First calculate the energy supply. Should be able to do that. Then after that, calculate the mass. Use E equals mc square. Can? Right. PT is the energy supply. Mc square is the conversion to mass. Okay, change your 10 minutes to 60 second times 60. So you should be able to get 4 times 10 to the power minus 13 kilogram. Can get or not? Just to get you warm up. Do all the use the formula E equals mc square.
Hello.
Okay or not?
Yeah. Okay.
Okay, let's go to checkpoint then. Checkpoint 25. $25.1. Okay, an example of a reaction study by Botti and Becker using a beryllium target as the nuclear reaction. Explain the difficulty of detecting neutron.
Like you said just now, neutron is a single particle, it has no charge.
Right? No, it is difficult to detect it because it is uncharged.
Yeah, that's why I just said no charge.
It has no charge. Hence, hence it produces very little ionization when it passes through matter, and it's not deflected by electromagnetic field. So we cannot detect it easily. To detect a neutron better, the neutron is slowed down so that it can be absorbed, such as in the reaction, neutron to boron, get lithium and helium. How does this help in detecting neutron?
The ejected alpha particle is easier to detect because it is charged.
The ejected alpha particle is easier to detect because it is charged. We can use the principle of conservation of momentum and kinetic energy to identify the neutron. Right? We can use bubble chamber to see the track. Then from there, we can use principal calculation using collision. Okay. In the experiment done by W. Botti and H. Baker, the penetrating radiation emitted was first thought to be gamma rays. How does it later found that the radiation was not gamma ray? Explain how the possibility of gamma ray is eliminated. Ken?
The radiation knocked off the proton.
When neutron produced is passed through hydrogen-rich paraffin wax, proton is knocked out from the wax. Proton can be detected. Momentum of gamma ray is very small, and its ionization power is very low. It's unlikely that gamma rays knock off proton from the paraffin wax. Right? And then we can use considering momentum transfer and conservation of kinetic energy in the collision between the particles. Chadwick conclude that the beryllium radiation was a neutral particle, which has a mass of about 1% more than that of proton. Okay with that?
Okay.
Basically, gamma ray is electromagnetic radiation. So at that time, it can knock off electron, like photoelectric effect, but cannot knock off proton. Proton is heavier. So it must be some neutral particle. Okay, let's go to checkpoint 25.2. Go and calculate this one if you haven't done it yet. It's better if you write in table form, then it's easier to calculate. Can neutral atomic mass of nickel is given. Find the mass defect, total binding energy, and binding energy per nucleon. First, calculate your mass of the total mass of proton, total mass of neutron, and add them up. Total mass of nucleon. Then after that, subtract the mass of nucleus. Then you get your mass defect. Can you get the answer? Cannot round off. Must use the same number of significant figure. Only round off at the end. Can or not? Can or not? Any problem?
Yeah, can.
Then how to calculate the binding energy per binding energy? Yep. How to calculate the binding energy? Right. This is in atomic mass unit. So to change the energy, use this conversion. No? Right. Since you are given the you are given straight away that value. No need to go to that formula. Right. Multiply by 931. Then you get 545 mega electron volt. Then how to find the binding energy per nucleon? Just divide by 62. Right? Binding energy divided by 62. You should get less than should get about 8 or less than 10. The highest is 8.8. Can or not? Can or not? Any problem? Anything not clear? Make an effort to do your homework. If not, you are losing your. You need to reinforce it. If not, you lose all that I teach you. Okay. Number 2, something wrong. Not enough information. Right? So cannot calculate unless you want to calculate this way lah. Okay, I think I will let the rest let you do yourself. Anything else you want to ask? If not, let us start a new topic.
Yeah, start a new topic. Teacher, there'll be no like half an hour break, all right? Just continuous, right?
Yeah. No point in a break. 1 hour class only. Okay, let's go to radioactivity. Let me just get the. Okay, let's go to radioactivity. Explain radioactivity decay is a spontaneous and random process. Define radioactive activity. State and use the exponential law. That's the law for radioactive decay. Define the decay constant. Derive and use the formula. Define half-life and derive the equation. Solve problem involving application of radioactive as tracer in medical physics. Okay, in your book is 263 radioactivity. Just summarize for you some of the things that we will be encountering. Okay, types of isotopes. We got natural isotopes, and then we can divide that into stable isotopes, naturally unstable and emits radiation. We call it radioisotopes. Right? There are isotopes that are stable, they are naturally occurring, they are unstable. Unstable, it will emit radiation. Then there are artificial. Artificial means man-made, produced by bombarding of stable nuclide with high energy charged particle. You can bombard with neutron or proton or even helium particle. So radioisotopes are isotopes of an element that is radioactive. When it's radioactive, call it radioisotopes. Background radiation, right? This is an approximation only. Different author will give different value. Natural radioactive isotope provide most of the background radiation around us. That's called background radiation. We are exposed to it, 37% from radon and thoron gas in the house. Gamma rays from rocks and soil on Earth. Radioactive elements in the body, we have carbon-14. Cosmic ray from space, about 14%. Medical, mainly from X-ray. X-ray used in hospital, 11%, 11.5%. 1.5% fallout, nuclear waste, and industry. So 87% from the first four natural radiation is about 87%. Is for sources, right? Others are man-made. Okay, that's just for your knowledge. What is radioactivity? Can define for me? Can? Right, that's the symbol. Where you go to any place where they use radioactive isotope, they will have a symbol there to warn you, just be careful. Right, that's why those working there have to wear a badge to measure how much radiation they are exposed to, so that you be careful not to be go there too often. Right? Radioactivity is the result of the decay, they call it decay or disintegration of unstable nucleus by emission of particle or particles, and sometimes accompanied by emission of gamma rays to form usually a more stable nucleus. Right? Basically, the nucleus is unstable. It want to become stable, so it eject particles, can be alpha, can be beta, can be gamma. Can alpha, beta, and when it emits alpha, beta, sometimes it will emit gamma rays also. And the original radioisotope, we call it parent, which is unstable. And then the product, we call it daughter. And then the emitter particle. Okay, we have the parent, unstable, transform to the daughter. Hopefully it's more stable. Right? Sometimes cannot, is still not stable, then it will disintegrate further. And then the emitter particle is the alpha particle, which we use detector to detect. Radioactive decay of nucleus is independent of environment of the nuclide. It doesn't matter where it is. It can be in a furnace, or it can be combined with another atom. But it can still disintegrate. Parent and daughter nuclei are different. These two are completely different atoms. We use different terms. Sometimes some books will call it decay, disintegration, or transmutation. Same, all mean the same thing. It's spontaneous and random process. What is a spontaneous decay? What is a spontaneous process? Can you still remember from the SPM? And what is spontaneous decay? Yep. Trini, are you with me or are you?
With you, Chair.
Yeah, what is spontaneous decay?
Spontaneous means impossible to predict which atom is radioactive lah. Which one would decay or not at an instant time or when particular atom would decay.
Is one unaffected by environment changes, such as temperature or pressure. It doesn't matter about the change in temperature or pressure. It just occur. It just occur. Right? Not affected by environment. How about random process? Yeah. How about random process? What does it mean?
Random process. It can it means has same probability to decay at that certain instant lah.
We cannot predict which particular nucleus will decay next. That's what it means by random. Any nucleus can decay. Cannot predict which one. It's one of constant probability of decay per unit time of the nucleus. Okay. How is the random nature of the emission shown on the curve? How do you know it's random? Random nature of emission from the curve itself. Reviewing with you what you have studied in your SPM. How do you know it's a random decay? From the graph itself. Graph shows exponential decay. How do you interpret that it's a random nature? Can remember?
No.
Random nature of the emission is shown by the curve being not smooth. It's not a smooth curve. Sometimes it emits more radiation, sometimes less in a particular direction. I remember when we measure radioactivity, we put a detector in one direction only. But if it's random, sometimes it will throw out the emitter particle in one direction, sometimes in another direction. That's why sometimes you get more in one direction, right? More in one direction, and then sometimes less in the same direction. That's why it shows like random. Right? CPM is count per minute. This one should be time, not reading. Time. Okay. How is spontaneous nature of emission? How do you know from the graph is spontaneous emission, or how do you show? How do you show the spontaneous nature? Right? Spontaneous nature of the emission is shown by the curve being identical for the same isotope. You can put in oven, and then you can measure the count rate when you put the isotope in oven, and then you can measure the count rate when it's in the room. Right? You change the temperature, it doesn't affect the curve. It still look identical. Okay. That's how we show it. The spontaneous nature of radioactive decay. Law of radioactive decay. Right? Rate of disintegration of a given radioisotopes at any time is directly proportional to the number of atoms present at the time t. Okay, that's a radioactive decay. You can measure it. So that's a law. Should be able to write it. dN dt equals to minus lambda n. Lambda is called the decay constant or probability constant. Stop me if I'm going too fast. Why negative sign? Yeah, why do we put a negative sign?
Negative. Oh, I mean to show that the number of radioactive atom in the sample decreases with time.
Okay, good. Negative sign means that as time increases, the number will start increasing. But this is not the case. Negative sign because as time increases, the number decreases. Good. Okay, let's look at the decay constant. Why we call it probability constant? Right? We write lambda. Okay, this one is small. Right? You can put a triangle there. Small number. And then take this n down. And then there's a dt. dt, we can call it delta t. Right? This is fraction decay or probability of decay. And then 1 over delta t. That one is per unit time. So decay constant is the probability of decay per unit time. Okay, dn or delta n, very small change in number of particles. Law of radioactive decay. Right? Lambda is fraction of the total number of atoms present per unit time. Right? Or per probability of decay per unit time. Either one. Or, right? That's what it means by fraction. Delta n over n. Probability of decay per unit time. Same thing. Right? Either we call that fraction or call that probability. Provided the unit of time is small. The time is small. Unit per second or counts per second or becquerel, BQ. Just to honor the scientists who discover radioactivity. Different radioisotopes decay at different rate. Right? Lambda is a constant. We can measure it in the lab. Right? Let's go to find the solution to the equation. Right? Remember, the original nucleus is called the parent nucleus. The result is called the daughter nucleus. And then the emitter particle. You have the emitter particle, three things involved: parent, daughter, emitter particle. Number of radioactive isotopes present at time t equals to is n equals to n naught E minus lambda t. I will derive this equation in a while. What is n naught? N naught is number of atoms of a certain radioactive isotope present initially. Right? The radioactive isotopes number present initially or at the start of the experiment. N is the number present, number undecayed after time t. Right? Remember that. Right? That's your, we are the one measuring this one per unit time, number per unit time. And this is a number present, parent number present. Right? With one fraction remaining, we just take n not down there, that's all. There's a fraction remaining. Must be able to play with the formula. Any questions so far?
No, sir.
Okay, if not, let's carry on. Okay, let's derive it. Derive the equation. If the number of radioactive nuclei initially is n naught, right? Number of atoms present initially is n naught, and the number after time t is n. Right? That's our equation. That is a law. Right? Take the n down, take the dt across, and then becomes integration. Right? Initially 0 time n naught, time t n, negative sign there. That's why we got negative sign there. Right? Integrate it. Solving it. Okay. For that. Then rewrite that. Right? Ln n over n naught equals to minus lambda t. And that's how we get our solution. Okay. Take the exponential or anti-log. Anything not clear? Yeah, talk to me, talk to me. Anything not clear? Okay, let's look at the decay constant. Decay constant and T half of a substance. Usually your book will use capital T lah. Right? Tend to use small t sometimes. It doesn't matter as long as you can understand. Okay, decay constant lambda T half of a substance are specific to the isotope of the element undergoing radioactive decay. Right? Is constant for particular radioisotope. For example, bismuth 210 undergo decay to Tl 206. Half-life is 5 days. Bismuth 215, by comparison, undergo beta decay to polonium with a half-life of 7.6 minutes. Yeah, you can see the different there. That's 5 days. That's 7.6 there. Right? Different isotope decay differently. Okay, next point to define is activity or intensity. Is defined as the rate of disintegration of the substance or the number of nuclei that decay per unit time. Okay, so activity equals to dn dt or delta n over delta t. Right? Remember our law, radioactive decay law. Okay, from that, dn dt we can write as, right? Don't worry about negative sign because activity is a positive value. And lambda. Right? So it's called counts per second or becquerel or disintegration per second. That's the unit. Right? Activity of a source is detected by detector. Right? We measure number of atoms detected per unit time. And lambda, 1 becquerel is equal to 1 disintegration per second or 1 count per second. Sometimes because the number is too high, we use another unit. Curie is defined as the quantity of radioactive material that undergoes 3.70 times 10 to the power 10 disintegration per second. Okay, so you should be able to draw the graph. If we start off with 100 grams of bismuth, half-life is 5 days. After 5 days, you got 50 left. After another 5 days, which is 10 days, 25 left. Right? After another 5 days, which is 15 days later, half of 25 is 12.5. After another 5 days, which is 20 days, half of 12.5 is 6.25. Right? You should be able to draw that. Okay, let's define half-life. Half-life is the time. It's a time taken for radioactive isotopes to disintegrate to half the initial number of nuclei. Okay, and it's given by this formula. Ln 2 over lambda, or ln 2 is 0.693 over lambda. Right? Let's derive this equation. You have to memorize it. Okay, we are going to derive this equation. Right? From our definition, if after a time called half-life, the number of radioactive nuclei remaining is half n naught. Right? Initially is n naught. After one half-life, it's half n naught. Then we go to the equation that we have derived. Substituting inside there, replace this n with half n naught. Replace this t with t half-life. Right? N naught and n naught cancel off. We take the reciprocal. Right? This becomes 2. This becomes positive. Right? And then take anti-log. Okay. That's how we get our equation. Okay or not? Anything not clear? Can or not? Can or not?
And
Okay. Alternative one is to use the definition. No need to memorize formula. Use the definition. There's your time. There's the number present at time t. Right? If we start with n naught, after one half-life, half of it will be left. Right? So if we start with that, after another half-life, right, another half of it will be left, half of this one. So we can write n naught 2 to the power 2, right? Same as that 2 there. So after n half-life, we can write as n naught 2 to the power n. Fraction of parent material that remains after radioactive decay can be calculated using the equation. Right? So we want fraction. As I say, we just take n naught the other side. Right? That's your n. Okay, and take the n naught down, you got this one. That's your fraction. N is the number of half-life. Time lapse, right? Time taken will be n times t half. Or you can use this formula, same thing. Right? Activity divided by original activity, that's the fraction remaining. Right? So exam, you can use either formula. Okay, that's the time. N times t half. Fraction decay. Okay, that's the fraction decay. 1 over 2 to the power n. Or we can use that. Okay, fraction decay, all these, you must know how to use them. Play with the formula to get all these. Okay, that's your number 17 in your worksheet. You can try out. Try out. We start with n naught. Sketch the graph. Right? We start with n naught. After one half-life, half of it left. You'll be able to draw your graph. There. Then after another half-life, half of 0.5 is 2.5, 0.25. Another half-life, half of 0.25 is 0.125. Right? After another half-life, half of that one. Right? Easy for you to draw on the square, half the square. and half the square, then you can sketch a graph. Can or not? Whereas the daughter is start with 0. Then after 1 half life, right? N naught minus 0.5, you still got 0.5. Same thing here. Then N naught minus 0.25 is 0.75. And N naught minus that 1 square. You still got 1 square behind that. Okay, can draw that. It's just opposite to here. Right? That is your maximum. This one, that amount. That one, that amount. That one from that amount. That one, that amount. That one is 1 square from the bottom. That one is 1 square from the top. That's how we draw daughter. Daughter is building up. Parent is decreasing. Okay, let's observe the graph. Number of daughter increases. Number of parent nuclei decreases. At half-life, number of parent equals number of daughter. The curve runs parallel to the time axis. That one. It goes to 0 at infinity, showing that the number of radioisotopes does not decrease to 0, but only at infinite time. It becomes smaller and smaller and smaller still. So usually after five half-life, we consider as negligible lah. Okay, natural logarithm, you use the formula. Right? If we take natural log of this one, you get this equation. And compare the equation of straight line. Okay, the graph is a straight line. There's your time. There's your ln n. Right? Plotting a graph of ln n versus t, you get a straight line. Okay, gradient minus lambda. Right? That point there, y-intercept. Your c is ln n naught. Stop me if I'm going too fast.
Yeah, teacher going a bit fast.
Okay, you stop me. Anything not clear? Anything you want to ask?
Not just so far.
Okay, the next
Are they like going to ask this in the exam?
Say again.
Are they like going to ask this in the exam?
We will be doing the exam paper after next week, after this weekend. I hope you will do your focus 24 for Friday.
24. Okay. Yeah.
No point going too fast if you don't do homework. After that, we will go to focus 25 next week. And then another hour, we will do partial paper already. We are too slow already. Okay, let's try to plot activity of a material that has an activity of 100 initially and half-life of 10 days. Right? Log linear graph. You don't need to know. This is for your info. Right? This easy way out for us to use this type of graph. Right? It's already plot for you, natural logarithm. So you can, this is one cycle. Right? So you cannot go to 0. You can use 1 here, 10 will be here, 100 here, or you can use 10 here. Then this will be 100. This will be 1,000. So if we start with 0 is 100, just for your info, you can catch it. This is an easy way out for us to plot it and show it's a straight line. Okay, this is a log scale. This is a linear scale. So it starts with 100. Right? After 1 half-life is 50 left. Right? That's 1 half-life. 50 left. Right? Is 20, 30, 40, 50. After another half-life, 25 left. Okay. Then we can just draw a straight line. Okay. Just for, as I say, that for info, easy way out for us to plot a graph rather than use a linear graph paper. Okay, A level they do have to know. Came out in AS, but you don't have to know. I think it's not mentioned in your syllabus. Okay, you won't bother about all that. Let's carry on. Okay, half-life, different value for different isotope. No need to memorize. Just understand that it can be very small or it can be very large. Varies from very small in second, to very large, millions of years. So if it's large, it decay very fast. If it's very small, it decay very slowly from that equation. Okay, your question 18, try this out. Try this question. Try this question. 18 in your worksheet. Activity of a piece of radioactive isotope is 4.3 times 10 to the power 5 becquerel at time t equals 0. The number of undecayed atoms in the material at time t equals 0 is 7.9 times 10 to the power 15. Calculate the decay constant. How to do that? What formula to use? Can tell me what formula to use?
What formula to use? T1/2 equals to
Basically, you want to find lambda. You are given A, you are given N. So the formula A is given, N is given, lambda is, you want to find lambda. So go to the formula A equals to N lambda. That's how we determine the decay constant for radioactive isotopes that have a long half-life. Right? Put in your value and calculate your lambda. So how to calculate your half-life? How to calculate the half-life? Just use the formula. Yeah. T half ln 2 over lambda. Put in your value. Okay, your answer. Write your unit there. Second. You can convert it to years if you want to. Any comment? Anything not clear? Do part C then. C part 1 and part 2. Can just use the formula only. There's only either 1/2 to the power n or E equals minus lambda t. Can or not, can or not, can or not, can or not. Okay. Use a formula. A naught over 2 to the power n. You are told for half-life. So n is 4. Okay, calculate your A. So calculate your A. Repeat this. And calculate your n. Can or not? Anything not clear? Talk to me. Anything that's not clear? Anything you want me to explain?
No, sir.
Okay, let's carry on. I think we should finish in a while. Right? Or you can use exponential. I think you can draw a table and do it. You know that from the definition itself, you started off with 4.3 at time 0. After one half-life, half of it left. After another half-life, half of this one is that one there. Right? Then the power 5 put it there. After another half-life, half of this one left. After another half-life, if you don't want to use formula, you can do it by the definition of half-life. Right? Half of this one. So that's your answer. That's all. Okay. Either way, or use A equals to A naught E minus lambda T. Either one. Right? Application to determine the age of ancient material, to determine force painting of about 200 to 300 years old, dating rocks and prehistoric fossils. Carbon-14 dating can be used to date objects to less than about 96,000 years, depending on the instrument used. Age of the Earth is estimated to be 4.54 plus minus 0.05 million years old. Right? This is based on the radiometric dating of meteorite using uranium lead isotope. How do we use radiocarbon dating? This is just for your info. Right? First, cosmic ray from outer space collide with atoms in the upper atmosphere, producing energetic neutron. The neutron, produce a neutron. The neutron collide with the nitrogen atom in the air to produce carbon-14 and a proton. Carbon-14 oxidized, that means combined with oxygen to form carbon dioxide, and is transported to the lower atmosphere. It mixes with the air there in the lower atmosphere. Right? Because carbon-12, carbon-14 also taken by the plant. Plants absorb carbon dioxide during photosynthesis and take in carbon-14 in a ratio similar to that of the carbon-14 atmosphere. Right? The first thing we assume is the ratio of carbon-14 to carbon-12 in the atmosphere is constant. As long as it's not changing, very soon the amount of carbon-14 to carbon-12 in the plant will be the same. And then the animal take the grass. Right? So carbon-14 enter the body. Right? Carbon-14 is formed and decay. It takes about 30,000 years to achieve equilibrium. That's the rate of production of carbon equals the rate of decay of carbon. If the Earth is millions of years old, that equilibrium is reached. Right? Then we can assume we can use carbon dating. But if the Earth is young, then we cannot use carbon dating because if we say that the Earth is about 6,000 years old, then we cannot use carbon dating. Right? Because it takes 30,000 years to reach equilibrium. But if we assume the Earth is billions of years old, then we can use it. Okay, carbon dating. Okay, when the plant die or the animal die, the carbon-14, it doesn't take in anymore. So the carbon-14 start to decay to nitrogen, right, by beta minus decay. So the ratio of carbon-14 to carbon-12, first of all, in the atmosphere is constant, in the body is constant. When it dies, the ratio start to decrease. Okay, use of radioisotopes in medicine, right? This is just for your info. Right? Don't need to memorize all of them. There are about 50 naturally occurring radioactive isotopes, and the rest are artificial, right? Man-made. We probably don't know all of the many uses these radioisotopes have or the benefits they bring to various fields. Right? We are still discovering it and using it. There are many radioactive isotopes that are very beneficial in application in medicine. For instance, radioactive isotopes are used for radiation therapy and for locating brain tumor. For instance, if you need to keep track of the activities of your organ, radioactive isotopes are also used here. Right? Here are some radioactive isotopes and the application in medicine. Right? Taken from a book. Since the properties of radioactive isotopes, such as half-life and the particle emission, are unaffected by external factors such as pressure and temperature, that's the key that we use. Half-life is constant, not affected by, you put in a body, it doesn't affect by your body, the environment, the pressure in the body or the temperature in the body. And even the chemical reaction doesn't affect it. Half-life is still there. Radioactive nuclides are suitable as tracer. Radioactive tracers are isotopes which replace stable atoms in a compound and therefore allow the path of the compound through the process system to be traced. We allow to put the isotope in, and then we can trace where it moves to which part of the body. Nuclear medicine uses radioactive isotope in a variety of ways. One of the most common is as tracer, in which radioactive isotopes such as technetium 99M is taken orally or injected or is inhaled into the body. The radioisotope then circulates through the body or is taken up by certain tissue. Its distribution can be tracked according to the radiation it gives out. Remember, it gives out radiation, can be gamma, can be alpha particle, can be beta, and we can measure it, can track it. The emitted radiation can be captured by various imaging techniques. Usually it's gamma ray, easier to detect. Through such imaging, physicians are able to examine the blood flow to the specific organ and assess the function or the bone growth. Radioactive isotopes typically have short half-life and typically decay before their emitted radioactivity can cause damage to the patient's body. So wherever we use radioisotopes in medicine, we make sure that the half-life is short so that it doesn't damage the internal organ in the process of emitting particles. Right? Make sure it's short and we can study within the time we are interested in. Therapeutic application of radioactive isotopes typically intend to destroy target cell. This approach forms the basis of radiotherapy, which is commonly used to treat cancer and other conditions involving abnormal tissue growth, such as hyperthyroidism. In radiotherapy for cancer, the patient tumor is bombarded with ionizing radiation, typically in the form of beams of subatomic particles, such as proton, neutrons, or alpha or beta particles, which directly disrupt the atomic or nuclear structure of the target tissue. Ionizing radiation introduces breaks in the double-strand DNA molecule, causing the cancer cell to die, thereby preventing their replication. While radiotherapy is associated with unpleasant side effects, right? person who go for radiotherapy will suffer the side effect. It generally is effective in slowing cancer progression, or in some cases, even promoting the regression of malignant tissue. Right? Basically, the cancer cell is growing, so you use this therapy, right? You destroy the cancer cell from growing. Right? Example, sodium 24 is used in medicine to estimate the volume flow in patient. Small amount of sodium 24 is injected into the bloodstream. Small volume of blood is drawn after a few hours. Activity of sodium 24 in the blood is measured, and hence the volume can be estimated. Okay, so all these are the things that you need to remember. Okay. Anything you want to ask? We have more or less completed.
I think, sir.
So I'll post it on YouTube. All these you need to remember, summarize for you.
Rewatch it back, sir.
So remember, Friday focus 24.
Focus 24. Okay, sir.
Then Saturday we'll finish our nuclear reaction. Okay, if you got no question to ask, we will stop here.
Yes. Okay,
So,
thank you, Acha.
Okay, have a good day.
No, Acha, you wanted to say something, Acha?
No, nothing. We have finished already. I already give you instruction already. Do focus 24 on Friday.
Focus 24.
And then Saturday we'll finish nuclear reaction. And then after that we'll do 25. So you should be doing focus 24 and 25 already. And try to catch up.
Okay.
Even your checkpoint also, checkpoint 25.2, 25.3, you should be trying that already.
Okay, sure. Thank you, Acha.
Okay, have a good evening. See you then. Bye-bye.
Bye-bye. Bye.